So we will be talking about the steady state error, and we started it last time, as you remember. We have a feedback system with unity feedback. Unity feedback means that the measurements are perfect so that the sensor that you might have here is just one, so it doesn't affect the result. So the output and the output is a function of the reference input and the disturbance W. Reference input is R and disturbance is W. And then something which is very important for us is the error signal, which is the reference signal minus the Y signal, which is the output. The difference between the input and output is the error, actually. We can find it from the following equation. I derived it the last time, so I don't want to re-derive it here. And we want this error to be 0, if possible. Okay? Well, you cannot achieve exact 0 for all times. This is E of S. The E of t is the time variable. Now, what you can achieve is the following. If you put a certain step input on your system, which is R, let's say this one, the yellow line, a good response would give you something like this red line, okay? And a good response would be a system that has that is stable, a system that is stable, whose time domain conditions are satisfactory, and on top of that, it should not have any steady state error. You should not have, for example, ask your, let's say, robot arm to rotate 90 degrees, and it shouldn't be rotating 60 degrees. It should rotate exactly 90 degrees. So this green line shows a response with steady state error, and the difference between the R and Y in the final case where things are settled is called the steady state error. Steady state error is therefore the Y RSS, steady state value of R minus the steady state value of Y. We want to make this error 0 if possible, and we want to minimize it in general, because this basically means that you are not achieving your final aim. You want your car to go with 90 kilometers per hour, but it goes with 80 kilometers, and the error is not something good. So we want this to be 0, and we want it to be 0 for different kinds of inputs. We will see it today. And then the tool for analysis of such things will be the final value theorem, that is the steady state error. Steady state value of any signal can be found from its Laplace transform by taking the limit, letting the s go to 0, and multiplying that signal by s times u of s. Okay, that's how we do it. And I gave you an example the last time. That was where we had stopped. This is true only if this. Okay, and one thing we should note is that the final value theorem is valid only if the system, the closed loop system, is stable. For unstable systems, this result, the final value theorem, does not make sense. So we will go step by step. It will be a little bit conceptually heavy, so you should listen carefully. As you might remember, we have two inputs. R of S, which is the reference input. And then there is the disturbance, W, which we call. We will go, disturbance is something we cannot control. It is like something from the outside. let's say the wind is a disturbance for our system, or external torques which you don't have control is a disturbance. External temperature is a disturbance. So this is something you want to eliminate if possible. But we will look at the effect of each of them one by one. That is, we will first the effect of R, then we will look at the effect of W. So the first case we will have will be let W equals 0, which means we have no disturbance. So we have just reference input tracking. This is a tracking problem. Okay? So the steady state error in this case is just from the equations above, 1 over 1 plus G times G of S times C of S. G is the plant transfer function, C is the controller transfer function, times R of S. Okay? Okay, so we will be looking at this. Now the input R of T is the reference input, as we know. It can have different, it can take different values. It can be different functions. For example, one possibility is that R of T equals 1 for T greater than 0. This is a step input, as you know. This is probably the most common input we are using. And its Laplace transform is 1 over S. Okay? Then it is possible to have R of T equals, for example, T, which is an input which is growing over the time, like this T versus R of T. This is again, T greater than 0. This is called a ramp input. And here R of S, if you take the Laplace transform of this, it's 1 over S squared. Okay? And in general, actually, you can generalize this. Any polynomial function can be an input. R of T equals, let's say, T to the K. Well, technically, we need this K factorial because it's for because of the Laplace transform. So it's a polynomial, let's say. It can be, you know, it's just a generalization. It's not very much used, but the Laplace transform of such an input is simply 1 over S to the K plus 1. Okay. If you look at this K, actually the K term here is 0, and the K term here is 1, if you like. Okay. So in general, this kind of input includes the step and the ramp inputs, which are the most common inputs. So we will look at the general case and try to find out results from here. So the general case is as follows. So R of T, we will say, is T to the K to the over K factorial, which means R of S is 1 over S to the K plus 1. Okay. This includes step input, ramp input, all kinds of polynomial inputs. Okay. From the above equation, the error term is then 1 over 1 plus GC of functions of S times R of S. But R of S is this, 1 over S to the K plus 1, S to the power K plus 1. We want to find the steady state error. We use the final value theorem. Final value theorem. I will use the shorthand FVT for that. The steady state error, which is the final value, can be found from the Laplace transform, which is S times E of S, which is limit S goes to 0 of S times 1 plus GC times 1 over S to the K plus 1. Okay. Now this S and this K plus 1 cancels. So what we are left with, the limit S goes to 0 of 1 over 1 plus G of S, C of S times 1 over S to the K. Okay. So let's look at the different cases. Remember that if you had K equals 0, we had R of S would be 1 over S, which is step input. Step input is our most common input, so this is a something we have most commonly. So the steady state error for the step input is simply this is 0, this goes away, 1 over 1 plus G of 0. Instead of S, we put a 0 there. 0, 0. Okay, that's fine. We found the steady state error for step input. What about if you have a ramp input? K equals 1. R of S equals 1 over S squared, right? So the steady state error would be, well, what would that be? K equals 1 here, so S to the K. So it will be 1 over 1 plus G of 0, C of 0 times 1 over S. 1 over, well, this, whatever this S, 1 over 0 it looks like, right? So actually, I shouldn't say S here, 1 over 0, because, or I should say, this is a question mark. So what is going on here? This looks like ESS goes to infinity. That's a question. Well, not really. We will see. In some cases, it might actually, but we will analyze this. It is possible that it doesn't go to infinity. Actually, it usually doesn't, but there is a, we have to be a little bit careful here. It doesn't go to infinity, actually, when either G or C has a free S term inside it, okay? When there is a S term, so that S term is going to cancel that S over here. We will see. Let's analyze a little bit more. We will do the following, define the following. This G times C I'll define it as L as a shorthand, okay? Now this L might contain L0 term, and it might contain some s to the n terms. These are called the free integrators. Why do we call it integrator? Because when you take Laplace transforms, the Laplace transform of an integral is the function, integral of a function is the function divided itself, the Laplace transform of the function divided by s. Okay, so in Laplace transform, notation, the integral corresponds to 1 over s, as you might remember, and the derivation is the opposite. It corresponds to multiplying by s, and integration corresponds to dividing by s. So this division by s's is called integration. If you have one integration, you have s to the 1. If you have two integrations, you have s to the 2. If you have n integrations, you have s to the n. Okay, one more thing. This is called the loop transfer function. L of s is called the loop transfer function. Or it might be called the open loop transfer function, if you like, but let's keep it this way. L0 is the same function stripped of its free integrators, if there are any free integrators. For example, let's say the controller is just a constant. Okay. And g of s is, let's say, 1 over s times s plus 1. Okay. So L of s is k over s times s plus 1. Or we can write this as L of s equals k over s plus 1. This is an s plus 1. Divided by s. So this term is L0 of s. Actually. Okay, so we have one free integrator here. In any case, let's continue now. Remember that the steady state error was limit s goes to 0 from final value theorem. 1 over 1 plus g of s c of s times 1 over s to the k, right? But we can write this as, from our definition, limit s goes to 0 of 1 over 1 plus L0 of s. This is the loop transfer function, L of s, so I can write this L0 of s over s to the n times 1 over s to the k, right? But this s to the n can be rewritten as follows. There has to be a limit, sorry. The limit s goes to 0 of s to the n s to the k. Now we see if somehow this s to the n cancels this s to the k, our steady state error can go to 0 or it can be finite. We will see. For example, if n is greater than k, we will have ESS will be 0, right? We can say s to the k here. If n is greater than k, well, these terms are not too important. You will have, and this is what we want actually, okay? This is, we want, if possible, we want the steady state error to be 0 for different kinds of inputs, and that requires well, that is somehow related to the number of free integrators in the system. We will see. So if you look at it, we have n greater than k gives ESS equals 0. If on the other hand n is equal to k, n and k are equal, so they cancel each other, we have will be 1 over L0 of 0. That is probably a finite number. Okay, because L0 does not have you know, free integrators in it or anything. It doesn't have free S terms. And if n is less than k, the steady state error, well, in this case, unfortunately, goes to infinity. Okay. Well, this is something important. We will see that this n term gives us the so-called the system type. And here we reach to another definition. System type. Well, at first sight, this looks very, you know, very complicated and very unintuitive, but it is the degree of polynomial. You get used to it, basically. Input k, for which, this is a which, this is a w, okay. For which the steady state error is a non-zero, let's say, but system type, this is related to the system type here. The degree of polynomial input for which the steady state error is a non-zero, but finite constant. So when the steady state error is finite, K gives you the so-called system type. And very roughly, we can say the following. System type is equal to number of free integrators in LFS. Okay. Now, this is roughly correct, and it's not always correct, especially when there is a feedback term. This is not correct. Okay. So this is, let's just remember that not always correct. It is correct if you have unity feedback, if the feedback does not contain a H term in it. Okay. But for most of the cases we will be using, this is correct. Just a second. Let me not draw this again. So I'll just, do you see what I am seeing here? Do you see a PDF file?
No hocam.
No. Okay. So I'll just, there is a table here, but I don't want to draw it. So I'll just copy and paste it here, if you don't mind.
Hocam, we momentarily saw it.
Huh?
Bir anlık gördük hocam tabloyu.
Okay. Anyway, you will see it more now. So this is the table. Well, it is for the step input, ramp input, and parabolic input only. This is a little bit confusing, but anyway, if you have a type 0 system, for a step input, the steady state error will be 1 over 1 plus Kp. I will just tell you what Kp, Ka, and Kv are. Let me write them down here. Okay. These are called error constants. This is the position constant. This is the velocity constant. And this is the acceleration constant. Actually, we will see that, LFS has to have at least one free integrator to have a finite value. So let me just write that note that Kp, Kv, Ka, they are all equal to actually L0 of 0. Okay. In any case, let's look at this thing here. For a step input, the type 0 system gives a steady state error. Okay? Some steady state error. What is this one?
Hojam, can you please say which page in the textbook this table is from?
Yeah, actually, it's not from the textbook. It is from somewhere else, but maybe I should have taken it from the textbook because it doesn't look very correct to me when I look at it. Okay, I'll just take it from the textbook now. Sorry. This doesn't look. This looks strange. Static type 1. Trouble is, I cannot find the. Okay, let's do it from somewhere else. This is a much better table. The other one was a little bit confusing, so I'll use this one. I guess it would be better if I had drawn it myself. Okay, so this is what we have. So for a type 0 system and step input, you have steady state error is 1 over 1 plus Kp. And yeah. And the errors, steady state errors, would be infinite for these cases. Okay. For ramp input, like let's say t times u to the t, the steady state error for a type 0 system would be 0. Sorry, it would be infinite. This is again confusing. But the error, these are the important things you have to remember. What is that? This basically means for a type 0 system and with a step input, the steady state error would be 1 over 1 plus Kp. Then for type 1 system with a step input, the steady state error would be 0. For type 2 system, it would again be 0. For a ramp input, for a type 0 system, the steady state error would be infinite. For a type 1 system, the steady state error would be 1 over Kv. And for a ramp input and type 2 system, steady state error would be 0. And for a parabolic input, you would have for type 0 system, you would have infinite value, infinite steady state error. For type 1 system, you would have infinite steady state error. And for a type 2 system with parabolic input, the steady state error will be 1 over Ka.
Hocam, would you please explain what is type 0, 1, and 2?
Okay, let's go from this definition, which is a little bit more difficult to understand, but I'll go through it. I'll give you examples. The system type is defined as the degree of polynomial input for which the steady state error is a non-zero, but a finite constant. Okay. Now, let's take examples so that you will understand this better. Let's say that we have a type 1 system. Okay. For a type 1 system, if you have a step input like this, the step response for a type 1 system, this is y of t, the steady state error would be 0. Okay. Step input. But if you have a type 1 system, if you have a ramp input on the other hand, and if your system is type 1, your response would look like this, so that there is a finite steady state error here. The steady state error, this will be 1 over Kv. So this is ramp input. Okay. But on the other hand, if you have a parabolic input on a type 1 system, like this is the input, and your response is going to be, it's going to diverge so that the steady state error will go to the infinity here. This is the parabolic. So this is type 1 system. The steady state error is infinite. Okay. For a type 1 system, the degree of polynomial for which the system gives finite steady state error is this one. This one, okay? Whereas let's say, if you take a type 0 system, the step response will look like this. This is the step input to the system. And your response will be there will be a steady state error. Okay. So ESS here is actually 1 over 1 plus Kp. Kp is defined above. For example, if you have a ramp input to this system, again, your response is going to diverge. It's not going to be able to converge here. This is y of t. This is r of t. And the steady state error will be infinity. Do you get the idea here? So this is the degree of polynomial input for which the system response well, for which the steady state error has finite value, basically. It is not zero, but finite. So type 1 systems, for example, have steady state error to ramp inputs and some steady state error. And that steady state error is defined as the inverse of the velocity constant. Okay. I know that this is at first sight conceptually it's a little bit heavy, but you get used to it, as I said. Secondly, the important thing is for us, remember that very roughly the system type is equal to the number of pre-integrators in L of S. For example, another example, let's say G of S is
Hocam, the second graph you take in the orange circle, so it is the type 0, right? Okay.
Yeah, this is type 0.
Okay.
K of S is, I don't know, 2s plus 1 over s, let's say. So, this is not K of S, this is supposedly C of S. So the loop transfer function, which is the multiplication of all these, is 3s plus 1 divided by s squared times s plus 1, right? So you have two free integrators here. As two free integrators. And the system type is 2 here. Okay. By the way, remember that at the beginning of the class, this was only for the R of S, W is equal to 0. If W is not equal to 0, we will modify this thing a little bit. But let's do it in the next hour, okay? So let's take a break here.